Hey, Wheaton North, Mr. Irgler here. Let's talk about Hess's Law. This is one of the most foundational laws and principles behind thermochemistry and thermodynamics. So let's dive in. Let's say that you're a chemical engineer and you're designing equipment to produce perfumes on a kind of industrial basis. So perfumes are often produced through what's called esterification. So we take an alcohol and some sort of organic acid, and you basically fuse them together. You have to use a catalyst to do this, but you fuse them together so you have the alcohol part and the carboxylic acid part, and you turn it into an ester. And the ester it goes from smelling like alcohol and vinegar to smelling like pears, which is actually quite phenomenal. So ethyl acetate smells like pears. You could use that to make, maybe a body wash or something smell like pears. You want to produce this on a massive scale, so you'd want to use something like this. These are mixing vessels that we would use when I worked at Avon. These can hold 1,000 pounds, maybe up to 10 or 15,000 pounds, depending on the model. And these are like almost 2 stories tall. So this is just a platform where you can add stuff in. Now, it's super important to know how much energy this reaction is either going to consume or release. Because let's say it releases a ton of energy, you're going to have to design the vessel to both withstand that heat, but also create a system to kind of pull the heat away. Maybe add channels of cold water that you could run around it or something to draw the heat away in order to keep it from overheating. So we have to be able to calculate how much energy is going to be required or released in a given reaction. And that's where Hess's Law comes in. So Hess's Law states that no matter what the mechanism is for the reaction, the total enthalpy change is still the same. All that really matters is where you start and where you end. If you go directly to the products, that enthalpy change would be the same as the sum of any intermediate stages that you might have. So H2 and H3 would have to add up to H1. And H4, 5, and 6 would have to add up to H1 because they both start and end at the same place. We've actually seen this before with things like these energy diagrams. No matter what your pathway is, whether you add a catalyst or not, it doesn't change your heat of the reaction, right? You're still starting in the same place and you're still ending at the same place. So if we can total up the products and the reactants, then we can figure out what that difference is. And that's basically what Hess's Law states. So if we have our reaction, we can actually calculate how much energy this is going to release or consume if we have the standard heats of formation. And this is something that you would find online or in the table. There's actually a table in your textbook that has them in the back. So let's go ahead and go through this example. Here's our law. So the total enthalpy is equal to the products minus the reactants, and here's our reaction. Now, so the total is going to be the products. We need to add all those up. So that's going to be the ethyl acetate and the water. Find those on the table and plug those in. Make sure you keep track of negatives. And then minus the reactants, which are ethanol and acetic acid. So you pull those numbers in, subtract, and you end up with actually -6 kilojoules or 6,000 joules. Now let's say hypothetically that you had the reaction written in the reverse way. So I flipped the products and reactants and I put some coefficients in there as well. I'll do this just to kind of show you what we would do or what it would look like. You would do the exact same thing. So now our products are the ethanol and acetic acid. And so notice that I also doubled them because there's a coefficient of 2. So you got to pay attention. If there's a coefficient, you got to take your standard heat of formation times that coefficient. Now my reactants are the ethyl acetate and the water. When you total those up, when you run those numbers, notice how it's different. It's positive, and that's because I flipped the equation, and it's doubled because I put 2 coefficients in there. So it's kind of like you can kind of think of the reaction proceeding twice over, right? Producing 2 moles of product instead of 1. It's going to have twice as much heat involved. Now, where do these heats actually come from, these enthalpies of formation? This -276, this actually comes from the formation of ethanol. So the degree, again, means standard conditions. So that's 25 degrees Celsius, 1 atmosphere, 1 molar solutions. And everything's coming from its elemental state. So a lot of times you'll see fractions in these reactions because we're producing only 1 mole of the given product. And everything's coming from its most common state. So diatomic, if it's a diatomic molecule. Couple rules on manipulating these equations. Let's say that this is our general equation that we'll use as an example. The more reaction you have, the more heat is produced, which is kind of what I just said. So if you do the reaction twice, it's going to double the amount of heat. If you flip the reaction, if you reverse the reaction, you have to flip the sign. So it goes from negative to positive. And if you multiply it by some factor, it could be a fraction or it could be a whole number, then you have to do the same thing to the delta H. So here I took it divided by 2, and so I divided my enthalpy by 2 as well. This comes in super handy when we're trying to find a target equation. So let's say that this is our reaction that we're gonna do, and we don't know how much energy it's going to produce or release, but we have this other thermodynamic data that we can use. We have to use this data kind of as puzzle pieces in order to match the target equation that we have there at the top. Notice that we have 2 carbons in our target equation, but only 1 carbon here. So we're going to actually have to double this equation. And if we double it, then we're going to have to change all the coefficients and then also double the enthalpy. Anything you do to the equation, you have to do to the enthalpy. What's next? We need to get our H2CO2 in liquid form. Notice the difference in phase. This is just gas to liquid. If you compare this reaction to our target reaction, we also need to double this one. In both of these cases, the species that we were interested in was on the correct side, right? The carbon was on the correct side on the reactant side. And here it's on the product side and it's on the product side here. So we don't need to adjust that. We just need to double it. So when we double it, we end up with twice the heat and coefficients in here. Now what about this last one? Take a look at that for a few seconds and try and figure out how we need to adjust this in order to end up with this target equation. The easiest way to see it is the waters. Notice that a water is a product here, but it's a reactant here. So we actually need to flip this one, and we need to double it because we only have 1 water and we need to get to 2 waters. So I'm going to double it and flip it, and it becomes this. So I've reversed the reaction. If I reverse the reaction, I also need to reverse the sign on the delta H and also double it because I doubled the reaction. We can think of these as like intermediate reactions. Anything that shows up on both sides can cancel. So the COs cancel and this H2CO2 gases cancel. The liquids don't cancel, and we don't actually want it to cancel because it matches the target equation up at the top. Go ahead and sum all that up and we end up with the exact same equation. Now what do we do with the delta H? It has to be the sum of all of these. It ends up negative, and so this is an exothermic reaction. Okay, you'll see a lot of examples like this where you're shooting for a target equation and you have to kind of manipulate all the pieces that you're given in order to end up at that target equation. If you have any questions at all, as always, write those down, bring them up in class, and we can talk about it there. All right, this is Mr. Irgler signing out.